Okay, so I've done this before, but it's been a while, so today you just have a video lesson. So a couple things I want to make sure. One, you should have a page with notes on it. I have condensed some of the slides, so I have a few more slides than you have on your page, so just kind of do your best to follow along. Two, please pause this. There'll be a few times where I get you started on a problem and I want you to spend a few minutes trying it out. Don't spend too long because I'm hoping you can get through the whole thing today, so I'll give some recommendations as we go through. But definitely take a few minutes and wrestle with some of the problems on your own. So just kind of have that understanding from the beginning. I will say this is chapter 10, it is circles. There are definitely a few things that are going to be like, I've seen this before, which is awesome. And then there's also going to be a few things that are new, so it'll be kind of a blend of the two. Today is a little bit more the introduction, but we will reinforce some of our terminology and vocabulary. So, starting off, we're going to make sure we've got the right definitions for circle, some of the parts. We're going to be specifically looking at angles and arcs today, and then talking about a few of the measurements that we can find related to our circles. That'll include some that you are familiar with and some that are maybe a little bit new. So as we jump right in, defining a circle, we have a set of points equidistant from a fixed point, and so we need to start with the center. That is our fixed point. Every circle is defined by its center, and then we need to establish a radius, and that is going to be the distance from the center. So you've got your initial center point, and you establish a distance from the center, that's your radius. And if you put all of that together, and you collect all the points that are that same distance away, we then get our circle. So the circle in and of itself only refers to the points that would appear on this curved line, and it is defined by the two values, where is the center located, and then where is the distance from that center. So all of our geometric shapes have a very simple definition. You might remember we define a line as 2 points. We have our parabola where we've got a vertex and some sort of a scale factor or a dilation. So we tend to only need a couple of values to define each of our objects. So for our circle, you've got a center and you've got a radius. Moving right along. We're going to identify a few different parts of our circles. So going down our list that you have on your page, first up, we have a chord. And a chord is any segment whose endpoints are on the circle. So right here, we would be able to say that we have chord AD. Now, because it is a line segment, we can define it as such, which means it'll be written with its endpoints, AD, and then a line over it. So that right there, we would be able to say is chord AD, and we would write it as a line segment because it is a line segment. Going down that list, we can get more specific and have a diameter, and what happens with our diameter, it is still a chord, but it adds as a qualifier that it also passes through the center. So we see this segment right here, A going down to B, is also a chord because its endpoints are on the circle, but it has an extra detail that it goes through the center. This is kind of like your square and rectangle definitions from chapter 7. You remember how a rectangle was 4 right angles, and then a square was 4 right angles and 4 congruent sides? It added an extra detail to be more specific. That's what's going on right here. So we would be able to say that in this diagram we would have diameter AB. So we've got a chord, we've got a diameter. This is going to jump to another slide, so I'm going to erase this part, but on your page it should be the same page. We're going to jump to another piece, and that next piece is our circumference. And the circumference, please erase. That circumference is simply the distance all the way around the circle. So that's one that we should hopefully be familiar with from years past. Basically, if you're on the outside edge, you're walking all the way around, how far are you traveling? So we do have that circumference. I'm going to go ahead and stop here for a second. Does anyone remember the formula for the circumference of a circle? Maybe, maybe not. So generally speaking, it's written one of two ways. In its simplest form, it is pi times the diameter, which you could also write in terms of the radius because it follows easily that the radius is half the diameter. So if we double our radius, we get our diameter. So we have that right there. I'll tell you up front for this class, pi can be left in your answers. I stressed all year that I like exact answers. So we're not going to be punching in 3.14 very often. Most of the time we're going to leave pi in there. There are a few instances where it's more appropriate to find the number value, but otherwise, just like how we've left square roots in our answers sometimes, and just how we will leave fractions, yes, fractions are our friends, we're going to leave the symbol pi in our answers as well. So stay tuned for that. We'll get some practice. And then more formally, yes, we've got pi right there, which is the ratio of the circumference to the diameter, which is basically the same statement up above, just flipped around. And so we've got all those values right there. And then just to write it another way, you could think about pi as being the circumference divided by the diameter. That's how the numbers have been determined by mathematicians over the years. Is, oh look, we measured the circumference with string. Oh look, we measured the diameter. And for whatever reason, all circles have the same ratio between them. As an approximation, it is 3.14, but like I just said, we are going to leave pi as part of our answer, leaving those answers exact. Okay? So it's a couple more terms right there. Already have it written down, which could also be written as 2r, which is what I had written down before. So kind of jumped ahead a little bit. It's been a year since I've looked at these slides, and apparently I predicted a little too quickly. So with that, we're going to use these two formulas right here, knowing that circumference is pi times 2 times the radius, and we're going to tackle these next two problems. So in this first problem, I'm going to do two things. Let's get a little more creative. Hello. Gonna be nice? We'll just go there. Alright, that'll work. Okay, so in this problem it says solve problems involving the circumference of a circle. Essentially it comes down to know your formula and just plug things in. So the formula itself wasn't too hard. We had 3 variables, 3 parts in a little ratio. So in this problem right here, we're starting with the radius, and they ask for both the diameter and the circumference. So if I come down here for a second, and I know that my circumference is equal to 2 pi r, or pi times the diameter, that's one relationship. And I also know that if I have my radius is equal to my diameter. Now think for a moment, where should I add a value? I need 2 radius, or 2 radii to equal my diameter right there. And so if my radius is 20, pretty easily we can determine that the diameter up there must be 40, because we need to multiply by 2. And if I know my diameter is 40, if I come over here for circumference, well sure enough, circumference is going to be pi times the diameter, or 40 pi. And that's the end of what you need to solve. So that right there is a quick little example. I'm going to put another one up on the board. And I'm going to want you to pause right now. I'm mixing this up a little bit. I'm giving you the circumference first. Take a moment, pause, try this one with your neighbor. Take about 30 seconds, and then hit play, and we'll give this one a go. Okay, so if we know my circumference is 100, and we know circumference equals pi times diameter, well, 100 equals pi times diameter. So in other words, diameter equals 100 over pi. We just found diameter. If I know what diameter is, and I want to take that diameter and turn it into a radius, well, I know that since my diameter equals 2 times my radius, I can replace diameter with what we just found, 100 over pi is equal to 2 times my radius. all I have to do is divide by 2, and in so doing, we get that the radius is equal to 50 over pi. And so we found both our diameter and our radius. Fractions, leave them. They're totally fine. So we got those values right there, no problem. Okay, so jumping right along, we can get way more creative with what's going on. Okay, so I'm going to move this up a little bit. Perfect. Downside of a cold classroom in the morning, the whiteboard doesn't want to work. But we move on. Okay, so circle P, the radius is 4. In circle T, the radius is 6. If QR equals 1, then find RT and AB. There's a lot going on in this picture, and a lot of times students get very confused very early. And so the key is, you gotta go piece by piece and draw on your picture. This chapter, you're gonna do a ton of drawing on your pictures. You have to. There's no way around it. So we're gonna go piece by piece. Circle P. Okay, here's P. So I'm looking at this circle right here. It says that the radius is 4. So I know that this radius segment, whether I go A to P or P to R, I know that that is 4. Okay, so I'm just going to label that on my picture. Circle T, the radius is 6. So I'm going to put it over here just so I don't mix them up. I know that that radius is 6. Okay, so far so good. QR equals 1. I'm going to grab another color for a second. Let's grab this purple one over here. And we got to be careful. Q. It almost looks like it should be going to this dot a little bit, but remember it was named circle P, so P has to be this point. So Q is really referring to this one over here. So they're telling us right here that QR, that's the distance, is equal to 1. Okay? And then it says find RT and AB. Okay? RT is this chunk over here, and AB is going to be going all the way across. So right away, I've got this in mind. I kind of need to find all the chunks going all the way across. Okay? So let's focus on RT for a second. First, pause. Spend a little moment talking with your group. If you guys get stuck, play the next moment. Give me another chance to pause after I give you a hint. Key that you need to remember. The radius can appear anywhere in your circle, as long as it's going from the center to the edge. So if I define the radius of circle T to be 6, if I go from center to the edge of the circle, that is also going to have the same radius of 6. So with that in mind, can we now find RT? Well, sure. RT is now your radius of 6 minus the overlap purple in 1, meaning RT is 5. Okay? Now when we go over here to look at AB, which AB is going to go all the way across. What I'm going to think about is I'm just going to build it piece by piece. I know A to P is 4. I know P to the edge of its circle is another 4. I know R to T is 5. And I know T to B is 6. So I'm just going to build my segment going all the way across. And so by doing that, 4 plus 4 plus 5 plus 6, 8 and 11, we get an answer of 19. Okay? And so the idea with these pictures is you just have to build and put your pieces together. Okay? So that's number 3 right there. There's another one right here. Same picture, says in circle P the radius is 4. I think this is just an extra slide actually. We already did the problem on the last one, so I'm going to just move on from this slide. I think it's an accident. Yeah, I'm going to go with it's next. It says page 3. There's another part here that says this QR bit. I'm going to skip this for just a second. we're going to go on to this problem right here. This one's a little bit different. If the radius of a bike is 17 inches and the wheel turned 10,500 revolutions, how far did the bike travel? Go ahead and pause this video for a second. Take a moment to try this with your groups, and then come back together to solve. So, starting with this problem. So, pause if you haven't already. Now, if you've come back, when I look at this problem and I've got a bike wheel, they're saying that bike wheel has 17-inch radius. And then from that information, they say that, hey, we're going to turn 10,500 times. And so basically, if I know how far it's traveled with one revolution, I can then figure out the total for the entire ride. And so if I focus on one revolution to start, that's just code for what's the circumference. So if I go right here, I know my circumference is going to be 2 pi times the radius, which is 2 pi times 17 inches. Okay? And so we could write that as 34 pi. Now, this is a situation where, hey, it makes sense to go ahead and turn this into a decimal. It makes sense that we're going to find an actual value. But we're going to wait till we get all the way to the end. Because this right here is a circumference of one revolution. So we know to get our total, we're going to have to take one revolution and times it by all 10,500. And so I can't do that in my head. So I'm going to come over here, grab one of the calculators. You can probably grab your phone for a second. I'm going to go 34 times 10,500. And we get 357,000 pi, and our units would still be inches, okay? And so if we found an exact answer, we could multiply that by pi. And I'm actually, just as a tidbit, going to be using the pi button on the calculator. If you're using the graphing calculators, it is going to be right above the caret key in blue, or the exponent button in blue. So you can look at that spot, because that's going to give you more digits than just 3.14. And so I get an approximate answer of 1121548.577 inches, which is kind of a lot. If you are curious, let's see, we can divide by 12 to get feet. We can divide by 5,280 to get miles. And it is roughly 17.701 miles. So it gives you an idea. I'll tell you up front, I really like that exact answer with pi in it. That will be my preference. But let's be honest, you're eventually going to convert it into something that's more meaningful, whether pure inches or miles. You're not going to go up to someone and be like, I rode 357,000 pi inches yesterday. Like, no one talks like that. So you need the exact answers to get to the moon and build your bridges, but when you're communicating with those around you, we tend to use decimal approximations. Okay? So that's kind of the first chunk. Moving right along, we got a few more definitions. So we're going to start by defining a central angle. Okay? So these angle relationships are going to be a bit different. So this central angle right here starts by identifying the vertex as the center and the sides as the radii. So I'm hoping you can see this angle right here. It has the vertex at the center of our circle, and the sides of the angle are radii of the circle. So both points A and B are on the circle. Okay? Now that chunk from A to B, that is called the intercepted arc. And I'm hoping that makes sense. If you've got a central angle and you shoot two radii off and it hits your circle, well, the part of the circle that's inside the radii is your intercepted arc. So you've got AB right there. A few more types of arcs, just to familiarize ourselves with some of the vocabulary. If we're looking at this picture right here, you have what's called a minor arc, And a minor arc is any arc that is less than halfway around the circle, and you will define it using 2 letters. So in this case, we have arc AB, and so I'm identifying it by the points that are on the circle and the arc. And notice the notation, it has a little curved line on top. Okay, it's not a straight line, it's a little curved line, and that would be read arc AB. Okay? If we have a minor arc, we can also have a major arc. A major arc is more than halfway around the circle, so in this diagram right here. And you'll notice we need 3 letters. So it's saying to go from A to D to B. The reason we need 3 letters is by arc notation, the rule is this. If I give you letters as an arc name, you are always going to take the shortest path to the next letter. So if I came up here and I tried to describe just arc AB, the reason I know it has to be this little one versus going all the way around the other way is because by rule you always take the shortest path to the next letter. And so in the case over here, I know A has to come down here to D, D has to come over here to B. And so that is just a convention that we use. What that means is all major arcs will need 3 letters in their name, and all minor arcs will only need 2 letters in their name. Just one more special case. Obviously you could have a semicircle, which is exactly halfway around the circle. To be specific, it will also need 3 letters, just because are you referring to the right-hand side or the left-hand side? I don't know. So in a case of being explicit and specific with our language, semicircles will also get 3 letters for their names. Okay. Finding measurements for our arcs. Arcs measures refer to the rotation or curvature, and they're specifically defined by their central angle. So in the case over here, the measure of angle AB, so if I want to give a measure to this arc right here, it is going to be a match to whatever the central angle is. So the measure of the arc matches the intercepted angle. Or sorry, I said that backwards. Measure of the arc matches the central angle. Okay? So obviously a semicircle is 180 degrees. And then just to be specific before moving on to the next example, because I thought I had something else on that page, but I didn't. The idea is that if I come over here, and there's my intercepted arc, okay? If I want to know the arc measure right here of AB, if I come over here and I know that this is 30 degrees, well then that's saying A to B would also have a measure of 30 degrees. So it's just a direct matching between the central angle and the intercepted arc. Okay? So we're going to take a look at a practice problem that has a little bit going on. Again, read through this for a second and maybe try it depending on the time that you have. I'm going to come right here and add stuff in. We're told that AD and BE are diameters, and we're told that ACB is 40. So we need to take a moment to just find the things down our list. So again, take a moment to discuss with your group, but I'm going to jump right in. So they start off and they ask for BD. So BD is going to be this chunk right here. And so here's what I know. If this is a diameter, then I know it's a straight line. So if this angle is 40, I know that because of supplementary angles form a straight line. I know that this angle is 180 minus 40, or 140. If this angle is 140, then its intercepted arc is 140 degrees. So I know that BD is 140 degrees. ABE. If I come over here, arc A, B, all the way around to E. So we're going here, and we're going all the way around. We're going big. Go big or go home. You got a couple ways you can put this together, and you can get kind of creative with this. I'm going to show you one way. Where my mind went to first was this. I know this angle is 140. These two angles are vertical, so I know this is 140. So I know this is 140. Well, how does that help me? I just found the part of the circle I don't want, right? I just found E to A is 140 degrees. Well, if E to A is 140 degrees, I know that I want everything else. Well, how much is a whole circle? 360. How much do I not want? 140. So what's left? 220. You could also add it up in pieces. You know this part in black is a 140. You know this 40 is going to become a 40. You can use vertical angles to move down, and so you know ED is also going to be 40, in which case you can add up those three values as well. So you can have a choice there for how to put it together. And then finally ED, well, I just kind of talked through it. This angle is 40. By vertical angles, we know this one's 40, in which case that piece right there also has to be 40. So we've got our values right there. The idea is that central angle matches the intersecting arc. Finding angle measure, we already kind of looked at this. There's one kind of idea that's really obvious, but it's just good to be explicit. And that is the idea that, oh look, you can add angles up. So it's called the angle addition postulate. We've used it with segments. It shouldn't be too surprising. And basically just says that if the arcs are next to each other, so there's J and A, no big deal, there's an arc. If I take the next arc A and B, oh look, there it is. Oh look, I can put them all together and call it JAB, or in this case JB, because it's still a minor arc. And so the idea is just, if you've got pieces of arcs next to each other, you can add them up. And so that lets us add things up and subtract. It's a very basic idea, but it technically is needed as a foundational rule, so we're going to toss that in there. Okay? So we've got that, no problem. This problem right here, I don't know where I'm on time. I'm going to go for it. So again, take a moment. You've got your pieces. AB equals 3x plus 12. AE equals 5x minus 8, I think. Yes, minus 8. Solve problems involving a circle with diameters AD and BE. So let's put this together. We know, find x given the situation. So AB is 3x plus 12. So we can come over here and we know AB is 3x plus 12. Okay? And then it also says that AE over here is 5x minus 8. So the question just becomes, how do we get to put those ideas together? And that comes from reading the first part of our problem. And so it tells us that BE is a diameter. And so if I know BE is a diameter, what does that mean about the two arcs that I have written in purple? Well, diameter cuts my circle in half. So those two arcs have to combine to make 180. So we can come over here and take our two pieces, 5x minus 8, plus 3x plus 12 must equal 180. And so we can go and combine like terms right there. We've got 8x plus 4 equals 180. Subtract our 4. 8x equals 176. So then x is going to be 20 would be 160, 22. Okay? And so the idea is you can put pieces together, and they take quite advantage, problems like these, about using the diameters and for stuff like that. So that works out pretty well. Okay? So that's right there. We're going to go on. We've got one more topic to cover. I'm hoping I can get this part done. We'll see. So the last thing we're going to take a look at is arc length. So when we talked about the degree values, that was arc measure. Arc measure is degrees. It is a reference for how much of the circle you have. Arc length is just that. It is a length. It is a linear distance. And so the idea is arc length is the linear distance from one endpoint to the other. Okay? So for example, I might recognize that part in purple as being, I don't know, 30 degrees, a portion of my circle. But depending on how big that circle is this circle on the floor in this classroom? Is this circle in the soccer field and it's gigantic? Is this circle part of a city or something of an even larger scale? Then depending on its size, the actual distance I have to travel if I were to walk the purple line from A to B might be drastically different values. And so that arc length can change. And so in order to find it, it is a piece of the circumference, and so we end up using the following. 2 pi r. Well, that's just the circumference. I know the distance it takes to travel all the way around my circle. What's this first part say? This first part's just saying, what fraction of the circle do you want? If this is the whole circle, what part should you keep? That's all this formula is saying. So central angle over 360 is the fraction of the circle that you want. And then 2 pi r is your circumference. And so more formally in this picture, you could write it as angle ACB over 360, but I'm just going to stick to that central angle statement that we had before. So, going to our last problem. We know that ACB is 40. So I'm going to come over here and write this as 40. Excuse me. We want to find the length of AB, given that we know BE is 20. So over here we know that BE is 20. Okay? So our goal is to find arc length. If it was arc measure, we would say 40 degrees, central angle matches intercepted arc, done. But it says arc length. So the parts that we need part of our circle, and then we're going to multiply it by the whole circle, or the circumference. So if we come over here, the circumference piece, let's do that first because we're pretty comfortable with that. That's our 2 pi r. And so in this case, if my diameter is 20, my radius is going to be half of that. Kind of belaboring the point a little bit because you're probably like, just use 20, why turn it into 10? That's fine. And so we've got our circumference formula right there, and then part of our circle. Really simple. We know the whole circle is 360, but we don't want the whole circle. We only want a piece of it. And how much of it do we want? Based off that central angle, 40 degrees. And so we can put that together, 40 over 360, I'm going to go ahead and simplify as 1/9. And so we can come down here and we've got 1/9 times 20 pi, just combining the 2 and the 10, and so we can finish this up and put 20 pi over 9 and keep an exact answer. And I guess technically we could throw centimeters on there because it is that linear distance. So, that was a lot. We kind of threw some vocabulary, we did a few calculations. The thing that you're going to see in circles is none of the calculations are very difficult, but there's a lot of stuff going on. There's a lot of few little pieces. So I'm hoping that didn't take too long in the class period. A page is going to be passed out with some practice problems. Spend a little bit of time on it, depending on how much class time you have. Think about spending about 10 to 15 minutes tonight. Keep playing with it. You are not expected to have it completely done at the start of class tomorrow. We will spend a little time in class tomorrow and then also be starting to discuss the next topic. So take note of that. If you've got a little bit extra time, it would be totally appropriate for you guys to keep looking at your last chapter exams that got passed back to you yesterday. So there's a little info. Hopefully that went pretty well. If not, we'll sort it out tomorrow. All right, bye.